derivation of Schrödinger time-independent and time-dependent equations. So we start with time-independent Schrödinger equation. The total energy of a system is total kinetic energy plus total potential energy. The kinetic energy is a half mv squared, and for potential energy we represent that as Vx. P, momentum, equals mass times velocity. If I square P, then I have to square mv squared. If I divide both sides by 2m, and I will get mv all squared over 2m, and that equals a half m squared v squared over m. Therefore, p squared over 2m equals a half mv squared, because the m here cancel one m over there. Now I can replace the a half mv squared with p squared over 2m here. Therefore, E equals p squared over 2m plus Vx. So what I need to do now is to make p squared the subject. I need to take away Vx from both sides and multiply both sides by 2m. So first I get minus Vx equals to p squared over 2m. Then I get p squared equals to 2m into bracket E minus Vx, close bracket. And this is equation 1. Particles can move in a circular or straight line motion. For a particle moving in a circular motion, and it will generate an angle theta, and if you're moving from point A to point B, and this particle here, when released, can travel in a linear velocity c. Theta is the angular displacement, omega is the angular velocity, and c is the linear velocity. Omega equals angular displacement over time. Therefore, angular displacement equals omega t. For straight line motion, you're going from A to B in that direction, and that distance is x. In that direction is called displacement. So x is displacement, which is distance with direction. So x is linear displacement, and c is the linear velocity. Sometimes c is called v. And so c equals x over time. And that is linear displacement over time. The wave equation of a particle in one dimension is xt psi equals e to power I of angular displacement. Psi is the wave function of the particle motion, x is the x-axis, t is the time, and I is the iota, a Greek letter, and that equals root of -1. So what we're trying to do is to convert the angular displacement into a function of x and t. We know that angular displacement equals omega t, and omega equals 2 pi f, where f is the frequency. But we also know that c equals f lambda, where lambda is the wavelength. If I make f the subject, so I get f equals c over lambda. And if I replace f here into there, therefore omega equals 2 pi over lambda c. But c equals x over t, and if I take the c here and replace it with x over t, omega will be equal to 2 pi over lambda x over t. So we can say let k equals 2 pi over lambda, and therefore get omega t to be equal to k x over t times t, and the two t's will cancel out, and so that will be equal to kx. So we get angular displacement equals to omega t, which equals to kx. If I move omega t to the right, so I'm going to get the angular displacement to be equal to kx minus omega t. So now I've transformed the angular displacement into kx minus omega t. That's a function of x and t. Now I can replace the angular displacement here with that. E to power I theta equals cos theta plus I sine theta. This is Euler's formula. So I need to change the I theta here and replace it with this one. Now that I've changed angular displacement to kx minus omega t, I can now differentiate the wave function with respect to x while t is constant. I also differentiate it with respect to t while x is constant. So this is now partial derivative with respect to x and partial derivative with respect to t. Partial because I'm keeping one of them constant every time. If you're differentiating an exponential function with respect to x, you get dy dx equals to, well, if you're differentiating exponential, you get the exponential back times the derivative of the exponent. If you differentiate nx with respect to x, you get n. So that's why you go to n. So you get a function back times the derivative of the exponent. We're going to do the same thing here. If we differentiate e to power I into bracket kx minus omega t close bracket with respect to x, then omega t will be constant. And so if you differentiate kx, you get k. So that will be k times I times the exponential function itself. So I'm going to differentiate psi with respect to x. And so I'm going to get equals I k e to power I open bracket kx minus omega t close bracket. And the partial derivative with respect to x will be equal to I kx psi, because psi is equal to e I to power kx minus omega t. And we've got that here. So I'm replacing the psi here with that. And that psi, we cancel that psi. Finally, we get partial derivative with respect to x equals I k. Now I'm going to differentiate psi with respect to t, which means I'll get a function back times minus I omega, because I'm differentiating minus omega t while keeping the kx constant, and we get equals to minus I omega e to power I into bracket kx minus omega t, and that will be partial derivative of psi with respect to t minus I omega psi. Psi we cancel out in both sides of the equation, and then we get partial derivative with respect to t equals I minus omega. For time-independent Schrodinger equation, we use partial derivative with respect to x equals I k. But we know that k equals 2 pi over lambda. Louis de Broglie in 1924 proposed matter wave that lambda equals h over p. P is the momentum, h is Planck constant, lambda is one wavelength. If I replace lambda here with h over p, so we get k equals 2 pi over h over p, and that will be equal to 2 pi over h times 1 over 1 over p. 1 over 1 over p is p, and that will be equal to 2 pi over h p. H bar equals h over 2 pi, and 1 over h bar is equal to 2 pi over h. So if I replace 2 pi over h here with 1 over h bar, I get a new value for k. So k will be equal to p over h bar. And so if I take that p over h bar and I place it here, then the partial derivative with respect to x will be equal to I p over h bar. Now I need to make p the subject, so multiply both sides by h bar and divide it by I. So I get h bar over I, partial derivative with respect to x equals to p. In the x direction with a hat on, that's called momentum operator. So this is the momentum operator here. So differentiating the wave function with respect to x, we give the momentum operator p. The momentum operator, which is h bar over I, partial derivative with respect to x equals to p. If I square both sides, I get h bar squared over I squared, partial derivative second order with respect to x squared equals to p squared. But remember that p squared equals to 2m into bracket e minus vx. So if I replace the p squared here with its value over there, so I get h bar squared over I squared second order partial derivative with respect to x will be equal to 2m open bracket e minus vx close bracket. Now I need to divide both sides by 2m, so I get h bar squared over 2mi squared partial derivative squared with respect to x squared equals to e minus vx. If I add vx to both sides, I'm making e the subject, so you get h bar squared over 2mi squared partial derivative second order with respect to x squared plus vx equals to e. But remember, I squared equals root minus 1 all squared, which equals to minus 1. So if I replace I squared with minus 1, so we get minus h bar squared over 2m second order with respect to partial derivative with respect to x plus vx equals to e. This is what we call the Hamiltonian operator. H with a hat is Hamiltonian operator, and that's the kinetic energy, total kinetic energy, and the total potential energy of the system, and that's Hamiltonian operator. So that would be the kinetic energy operator. So now if I write the Hamiltonian operator, h bar squared over 2m second order partial derivative with respect to x plus vx is equal to e. Now I'm going to put a square bracket there, that's the Hamiltonian operator, and I'm going to multiply that by a wave function psi, and I'll multiply the other side by psi. And so now I can write this as h bar psi equals to e psi, and this is what we called the time independent Schrodinger wave equation, which you might call TISE. And the reason why this is called time independent is because we don't have t in this equation. There's no time in the equation, so it's time independent. Sometimes the second order partial derivative can be written as nabla squared, and the square indicating the second order, and that is basically the partial derivative squared with respect to x. And this is for 1 dimension, and if it's for 3 dimension, it will be plus partial derivative squared with respect to y plus partial derivative squared with respect to z. But for 1 dimension, this is what you write. So the symbol here is called nabla or del. And now we can write the time independent Schrodinger equation using nabla. It's going to be minus h bar squared over 2m del squared plus vx. Then we can put psi, multiply everything by the psi wave function equals to e psi. So these are the ways it might be presented, either that way or that way. For time dependent Schrodinger equation, we write partial derivative with respect to t equals to minus I omega. But we do know that omega is 2 pi f. In 1900, Max Planck and 1905, Albert Einstein both proposed E equals hf. Now if I replace E over h with f here, so we get omega to be equal to 2 pi over h times E. And we know what 2 pi over h is, so that would be E over h bar. H bar is reduced Planck constant. So now I can take omega and put it back here. So remember, this is omega, omega, and therefore we get partial derivative with respect to time equals minus I E over h bar. And if I make E the subject, I get E to be equal to minus h bar over I partial derivative with respect to t, and put a hat on it, that will be the energy operator. So differentiating with respect to time gives you the energy operator. So now I'm going to replace the E in the time-independent Schrodinger equation with this value. First, I need to rationalize the denominator. In the denominator, I've got plus I. I need to multiply both numerator and denominator by the conjugate of plus I. The conjugate of plus I is minus I. So let's look at 1 over I, and that would be multiplied by 1 times minus I, the conjugate of I, divided by I times minus I, the conjugate of I. And minus divided by minus is plus, so I get I over I squared, which is minus I, because I squared is minus 1. So 1 over I is minus I. Therefore, I can rewrite the E value, the E operator, to be, well, minus times minus is going to be plus, so that will be h bar, partial derivative, I h bar, partial derivative with respect to time. And that's the energy operator that we get from differentiating with respect to time. Now I'm going to replace the E with this value. So now we know that minus h bar squared over 2m partial derivative second order with respect to x plus vx is equal to E. Now I need to replace E with the value. So we know E equals to I h bar partial derivative with respect to t. Therefore, we get minus h bar squared over 2m partial derivative squared with respect to x plus vx. Well, let's multiply everything by psi, and that will be equal to, well, E is I h bar partial derivative with respect to t multiplied by psi. And so this is time dependent Schrodinger equation. So we can write it as time dependent Schrodinger equation, which you might call TDSE. Time dependent Schrodinger equation, because this one has time in it.